It's really good to be speaking to you today. It's incredible to see how this community is growing from year to year. So let's get started with a seemingly straightforward question. Who here likes abstraction? Show of hands, please. All right, okay. And who here does not like abstraction? This doesn't match up. Okay, so who here worked with code like this before? Yeah. And enjoyed the experience? Nah. I'm sorry. I don't want to bash on anything, but I couldn't resist. So now seriously, our background marks our present and shapes our future, right? We go forward based on the experiences of the past. But to many of us, abstraction, design patterns, and all other sorts of bureaucracy, usually found in classic O languages such as Java or C++, is something to be avoided, like it's a pitfall that we fear. And this is a trend I've been perceiving in the Go community. This obsession with extreme pragmatism when sometimes we should consider things a little bit more. But this is totally understandable, totally understandable. Some of this background steered Go's design to the realms of pragmatism, simplicity, and orthogonality. So it was a big success, right? It reached all of us here today. We wouldn't be here otherwise if it wasn't successful. But perhaps controversial, the thesis of my talk today is that careful use of abstraction, design patterns, and other sorts of software engineering principles are completely compatible with Go's philosophy. So Mr. Pike here has this quote, which I'm going to base my thesis on. I'm going to quote it out loud. So, unlike C++ or Java, which are about type hierarchies and taxonomy, Go is about composition. Okay. As we'll soon see, hopefully at least, composition isn't mutually exclusive with abstraction. To abstract is to take away. To abstract is to extract. And guess what? Designing robust software is taking things apart to the very simplest essence. And programming robust software is taking these things and putting them back together. So, all right, let me ask you something. Who here thinks that simplicity is easy to achieve? Okay, no one raised their hand. This is good. So I'm not going to ask the next question, which was the reverse. Who here thinks that simplicity is not easy to achieve? Great. This is the Go community. All right. So in the interest of longevity, of software longevity, simplicity is definitely worth striving for. And if your software is built for the long run, this is something you should consider every time. Go is rooted in this very simplicity. It provides and promotes the simple orthogonal constructs that we all love to use. But it does not promote unjustified avoidance of abstraction. In the end, if we are not going to take things apart to their very simplest essence, if we're not abstracting in the sole interest of pragmatism, we won't be able to evolve our software in the long run. Okay, so abstraction is not inherently evil. Used in the right way, it will make the constructs in our programs composable, and that's what Go is all about. So I want to exemplify how we can apply and extend these principles in our own code, in our software, not just the Go language itself. And together with you, I want to climb the abstraction ladder. I know it's a bit dramatic, but this is what I want to do today. So let's get started. OK. Who here? Where's my bottle of water? Everyone took my water. Thank you. So who's written code like this before? Show of hands, please. A few hands. Yeah. OK. So this is pragmatic, right? It's obvious. It's the obvious approach to putting all of these concerns around a normal HTTP client. Concerns here are logging, instrumentation for monitoring, authorization, a form of fault tolerance with retries, and some client-side load balancing. So as you've seen in Peter's talk yesterday, these and other orthogonal concerns are paramount in any serious production setting in a modern enterprise. But please note, like, production code would actually be more complex and long, and it would have even more surface for unexpected interactions between these orthogonal concerns. So this is the point that I want to illustrate. All of these things can be seen as separate layers of behavior. They are orthogonal to each other. But here, they're all twisted together. And so the more things we add, the more complex everything is going to be. You cannot consider one thing at a time. You have to think of all the weird interactions that it can have. And that was just an example, but in real code, things get out of hand easily. So we're, in fact, breaking the first principle, or software engineering principle, which I'm going to state today, which is the single responsibility principle. And I feel a little bit dumb asking this question, but OK, who here remembers what the single responsibility principle is about? I was expecting more hands, but so we'll define it anyways. So it's very obvious. The single responsibility principle states that a software entity should have a single responsibility. So how can we separate these orthogonal concerns into simple and composable constructs? How do we limit the large surface of unwanted interaction between them? Any ideas? Think about it for 5 seconds. OK, 5 seconds. Maybe it was a little faster. I'm pretty sure some of you have guessed it. We have to embrace the interface. And that's this talk's title. And not just about in any way you might think of. If we want to reduce the possibility of unexpected interactions between all of these orthogonal concerns, we need to reduce the scope of our interfaces. We need to make them small and precise. Single method interfaces, in my opinion, are the most expressive and composable tool of abstraction that Go has to offer. If we don't do this, or if we extend the scope of our interfaces, we're prone to violate the second principle of today's talk, which is the interface segregation principle. OK, I'm going to target you all Java programmers. Who remembers what this principle is about? Show of hands, please. I see one person. Interface segregation principle is just a fancy way of saying that client code should not depend on methods it does not use. So if you make your interfaces huge and with different methods, it's very likely that someone who's going to use that interface is going to have access to functionality that it does not need, and that possibly you don't want them to use. So make your interfaces small. Now, the benefits of single method interfaces go beyond just that. In Go, they coexist with functions as elegant and very powerful duals. This is possible in Go because any type can have methods attached to it, which enables function types like this to implement single method interfaces by calling themselves. This is one of my favorite parts of Go. Along with functions, anonymous functions, and closures, this duality enables some very elegant techniques inspired in functional programming, in languages such as Haskell or Clojure. And this fits very naturally with Go. Now, what is this? It's an onion, yeah. 2 onions chopped up. So what can we cook with these interfaces and functions? What can we cook out of this? I really hope onions don't make you cry because we'll be chopping some up. Sorry for the bad jokes. This is the decorated pattern. I must be killing you all now with principles and patterns and, well, we'll see. My thesis is that this is completely compatible with Go's philosophy. Did anyone see this pattern in other kitchens? OK. Anyways, let's define it. The decorated pattern, or the onion pattern, as I like to call it, is a design pattern that allows behavior to be added to an instance of a type without affecting the behavior of other instances of the same type. In Go, this is really easily expressed. Is this, you have a function, takes a client, or any interface, in our case, is a client, and extends it and returns the same type. But this type within the function has been extended. Its behavior has been enriched. This pattern helps us conform to both the single responsibility principle and the third principle of today, which is the open-closed principle. Java programmers again, what is the open-closed principle? Who remembers what this is? OK, the same person as before. Yeah, so let's define it. The open-closed principle states that software entities should be open for extension, but closed for modification. This sounds a little weird. That is, such an entity can allow its behavior to be extended without modifying its source code. How do we do this? This is the decorated pattern. It allows us to do this in Go with no bureaucracy. In Java or C++, this would be quite a lot of code to do. So let's see how we can get all of these interfaces and closures and onions into some tasty functional code. All right, so the first concern that we've seen in that piece of code before that we're adding to the client was logging. This is very common concern, very simple, universal need. And most of the time, you look at your production software, you have like all these log calls everywhere. You know, it's just littered with log calls and all of these things mixed together. You know, it's not the worst thing in the world, but I think we can do better. So let's see how we can add logging to a client without modifying its source code. All right, I'll give you 5 seconds to look at this while I drink some water. Yeah, this might require a little bit of focus. But before we build upon this explanation, I want to get a sense of who here intuitively understands this code. OK, quite a lot of people. It's good. For the other people, I'm going to try to explain. So a quick explanation. Closures are functions with environment. They're basically stateful functions. And in here, we're doing dependency injection of the logger, which is going to be part of the closures environment. So the original client, when applied to the decorator, which we return here, is going to become this new client, which is a function which implements the interface, which is just itself prepended with logging. This is what it will become. OK, let's take a deep breath. As I said before, simplicity isn't necessarily easy, and you all agreed with that. So this is true. But this code is responsible for a single concern. OK, once the mechanisms are understood, there is nothing else to consider besides logging. Next up, we have instrumentation. As you know, production software needs to be monitored. We need to instrument our code. If you don't use Prometheus, you should. Bjorn Stolk yesterday talked about it. Now, back to the subject. Just like logging, this usually ends up all convoluted within your code in huge functions, and things are not well factored. But fear not, decorators come to the rescue again, and just like the previous one, we have the same structure here. But instead of running something before we call the inner client, we defer a function to execute after it finishes. And so here we just have like two types of metrics which we inject, request counter and a histogram, and we add observations to it after the client finishes. All right, fault tolerance. This is a common need in distributed systems. We need to tolerate transient errors, transient faults, and a common implementation of this is just to retry something with a backup strategy. And this code does exactly that. So the decorator just attempts to execute the inner client until it doesn't get any error, and then returns the response. Otherwise, it will sleep for a certain amount of time, which increments on each attempt. Yeah, that's it. So notably, when you do something like this, you need to consider the semantics of the requests you're sending. You need to be sure that you can retry these requests that are idempotent. In production code, you'd probably also not do this for every error, but you classify the errors and just do this on transient errors, which you're confident that they are. Otherwise, you'd be wasting resources in fatal or unrecoverable conditions. OK, 2 more to go until we have this code refactored. This is authorization, common concern. We need to authorize our HTTP requests. We pass a token to it. So before, we had like this token in the client struct, and you just add it. Over here, it's the same pattern. We just generalized one of the functions to be a header decorator, so you can add any header to your client before it sends a request. And then we reuse this for the specific authorization decorator, setting the key to the authorization header of the HTTP spec, and then the token to the value that you pass in. In functional programming lingo, this is called a partial application but that's another talk. OK, last concern, load balancing. Load balancing, in this case, we just get a function in, which is, I call it director, which modifies an HTTP request to direct the request to a different backend every time. And we have 2 kinds of directors. We have round robin, which is a classic algorithm. This is all very naive. It's not really production code. It's to illustrate the point. But round robin, you just go around, choose a different backend every time this is invoked. And on random, you just pick one at random every time. OK, so all of these concerns are now completely independent constructs. But how do we compose these simple and orthogonal constructs into a coherent whole that satisfies what we had before? Well, there's a couple of different ways, but here's one I like. This function is called decorate and matches up the decorator pattern which we talked before. Gets a client, gets a list of decorators, and iterates over them and applies wraps with 1 layer of behavior on every loop invocation. We could write this recursively, but it's not worth the effort here. So we remember that onion that we've seen before? We have the core object, and we want to apply these layers of behavior. And this is exactly what we're doing here. We're creating this onion. The client, on the other hand, is left unchanged. So We are conforming to the open-close principle, to the single responsibility principle. And since our interface is so simple, also to the interface segregation principle. So our software can be composed. Our client, sorry. We're taking the default HTTP client from the standard library, which implements the interface that we defined, and we decorate it first with authorization. We just, it's just a random token. Then we need load balancing. So let's add load balancing with a round-robin strategy, starting on the first backend and going over. Logging. Now, all our requests are going to be logged with this prefix client. This is just the standard library logging. Now, we want instrumentation, so we're instrumenting our code. This counter and histogram are part of GoKit metrics package, which uses Prometheus under it in this. At last, the last concern, we had fault tolerance. So all of these orthogonal concerns, we split them apart into one thing, and now we're putting them back together. So we designed our software, and now we are programming it, we are composing it. And this fault tolerance just means like we can tolerate like five errors, and we sleep a second, and then 2, and then 3, and then 4. Okay, so for me, personally, when I discovered this pattern, I was mind blown, and I didn't know that this was called the decorator pattern. I kind of arrived at it by myself. But then Tyler, who is a colleague of mine at Mesosphere, thought, oh, that sounds a lot like Python decorators. Oh, what's that? Like, I went to check, and I discovered that this pattern already existed. And so we arrive at what we are at today. Anyone remembers or has seen this pattern in Go code? Quite a lot of people. Yeah, and so the common canonical example is the HTTP middleware server, which is a form of the decorated pattern. I think this is a great pattern to be applied in a lot of places, not just the HTTP package. So, in this talk, we've seen that very careful use of abstraction and design patterns and other software engineering principles can be entirely compatible with Go's philosophy of composable and simple and orthogonal constructs. The ideas presented in this talk aren't new in isolation, but I thought that it might just be inspiring in composition. And you know what? You can compose these things too. Don't be restricted by the pragmatism that sometimes could plague you. But be careful. Don't go all the other way. So what I want you to do is to find the right balance of pragmatism and abstraction and the lessons that we learned from the past. So remember, next time you pick the pragmatic hammer, just stop and consider the tools of abstraction at your disposal. Take the time to properly design your software. Take the time to break each piece apart to its very essence. If there is a long run, it will pay off. Thank you.